Welcome back, everybody. Today we are talking about molecular geometry. That is the chapter for today. So, real quick, we did talk about Lewis structures. So, we learned how to do those Lewis dot structures. But the reality is that a lot of chemicals, basically all of the chemicals, are not flat, right? They are not 2D like we've been drawing them. So this chapter is going to introduce you to molecular geometry to show you that molecule compounds that we've been learning about and the bonds that we've been learning about do not occupy flat structure. They're going to be a 3D. I think I have a molecule here, right? So it's kind of like this. So this carbon right here, instead of drawing it flat, is going to occupy a 3D structure. So what we're going to be learning today is, can I figure out the geometry from a 2D structure? After I've drawn the Lewis structure, can I figure out the geometry? That's the first thing. And then we're going to learn about something we call hybridization, which is the orbitals that result into the combination of these compounds. So we're still learning characteristics or chemical compounds. But today we're looking at the structure. So let's get started. All right, so this is chapter, right? So draw something real quick. So to give you an example again, let's do like CH4, right? C and so let's say I have CH4, right? So we learn how to do the Lewis structure, and then if you do it correctly, it should look like this, right? CH4 should look like this. And then after this, what this chapter is telling you is that it's not flat like this. It occupies a 3D shape, right? So instead of CH4 to be like that, it will be like something like, it's hard to draw it on 2D, but it will be like that, right? The hydrogens will kind of push away each other because there's nothing restricting them to one layer. So they are going to push away into each other so that they are stable. This is what we call a tetrahedral. All right. So let's talk about molecular geometry. Right. So if you take, again, if you take something like, and I'm going to give you a lot of examples so that it helps you to do it in the future. But if you take something like AB2, this is an example. What we mean here by A is the middle atom, B is the outer atoms, right? And I want you to realize something here. We're going to give you the number of atoms bonded to the central atoms and then the number of lone pairs. Why do we care about that? Because we're going to have two types of geometries, right? We're going to have an electron geometry and then a molecular geometry, right? I want everybody to understand this. I want everybody to understand this. Why? Because the molecule will not involve the electron pairs. But unfortunately, the electron pairs are going to be involved. But we're going to go up to it, right? So at first, we're going to use the chemicals that do not have electron pairs on them, meaning that you have just A bound to two B's. If you have A bound to two B's with no pairs, the geometry is called linear, and then the electron geometry are also called linear, right? That is the electron geometry, or the first electron geometry. So an example is barium chloride, right? This one is bound to two things, no pairs, so it is linear, right? And we realize that the angle is 180. We care about angles, right? Now let's go to the next level. The next level is What if it's one thing bound to three things, but no electron pairs? It's like a triangle, right? It's like a triangle. You have something in the middle with three things around. It's called a trigonal planar. Trigonal planar. So when it's a triangle, it's a trigonal planar. And it's planar because it's on one plane. It's like a triangle, right? So an example here can be like boron trifluoride, right? So boron trifluoride is an example. You realize that the angle is 120 because they are spaced apart like that, right? And if you go back to the periodic table, you will see that boron has three electrons. So it makes sense, right? It makes sense that it binds to three things like this, right? So this is the geometry of boron trifluoride, right? What if it's four things? Four things bound see, can you hear me? Hello. Okay. If you take one orbital and then you add another orbital, what you end up getting is a hybrid. The hybrid of two orbitals. All right. So we call this a hybridization. So if you take s orbital, right, an s orbital, you add p orbitals, and the p orbital will have three shapes, right? S orbital, you add p orbitals, you're going to get something called an sp hybrid, right? sp3 hybrid, because it's three of them, right? So this is a hybridization, and this is kind of giving you the idea of what we're going to get. And this is important, by the way, because it relates to geometry, right? If you have a sp hybridization, then you have a linear sp. So we have a few hybridization here, and let me give you a table, because sometimes it's harder to know which hybrid is which. So this is something that I got from the internet, and this is very easy, right? So these are different types of orbitals, and from the orbitals we're going to get the geometry of the electron geometry and the molecular geometry. But look at this, right? Think of orbitals are just like things bound to the central atom, the things bound to the central atom, right? So if, for example, you have two things bound to the central atom, you have sp orbital, right? If you have three things bound to the central atom, you have sp2. If you have four things bound to the central atom, sp3. Five things, you have sp3d, because you don't have sp4, right? Because p only has three. And then you have six things, you have sp3d, right? So if I ask you like the hybrid, I don't want you to get confused in geometries. Now, the geometries are good and are important to understand what is happening, but they tend to confuse people more than they help them, right? But again, what ends up happening is, first of all, let's say NH3, right? NH3. NH3, if you had to write down the electron geometry of NH3, you already know that it's S2, S2, sp3, right? And then if you have to do NH3, guess what happens? The hydrogen that usually has one S1, because it is one electron, what ends up happening is that this S of hydrogen is going to bind to this, right? Does that make sense? So this is the same thing, by the way. This is the same thing of like, okay, if I have N, the outer layer of N, if you remember, so N has 7 electrons, so it will be 2 here and then 5 here, right? 1, 2, 3, 4, 5, right? So the way I showed you this is the same way that you can do it with orbitals. And then hydrogen, same thing, right? Hydrogen, you have hydrogen here, then you have hydrogen here, right? So one electron of hydrogen would bind to one empty slot of nitrogen, same with the other ones, right? So it's literally the same thing as these, right? You have 3 empty slots in the pocket of nitrogen, and then the 3 hydrogens bind here. This is how we make a hybrid, right? A hybrid. And again, if I ask you what is the hybrid of NH3, you are going to tell me that, again, is if it's bound. So N, look at this, and because we're looking at electrons, remember, for hybridization we look at electrons, not just atoms. We look at electrons. So for NH3 we're going to take N here, hydrogen, 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 and then if you remember, you have a double bond. This is the Lewis structure. So after you draw the Lewis structure, you're going to count the things around nitrogen. 1 2 3 4. If it's 1 2 3 4, what will be the hybridization for NH3? It's sp3, because it's bound to 4 things. sp3. So if it's bound to 4 things, sp3, bound to 3 things, sp2, bound to 2, sp, bound to 5, sp3d, bound to 6, sp3d2. All right. So again, to give you an idea of how it looks like, right? For example, the sp2, right? sp2 kind of looks like this. Let's look at something a bit more complex, like ethylene. Ethylene will take 2 carbons, right? 2 carbons here. So ethylene is CH. Ethylene is C2H4, right? If I ask you to draw the Lewis structure for ethylene, it's going to look like this, right? C2H4. So the hybridization here is a bit interesting, right? Because again, you have the carbon bound to hydrogen, so you have the S, the hydrogen is S. If you remember, this carbon has 3 P's, right? 3 P's here. So this is P with 3, and then you have S, right? So this is sp3 and then sp3 here, right? So what ends up happening is, again, you have these bonds, right? So you have these bonds inside the plane, right? You have these bonds inside the plane with the carbons, right? But then you have these other pi bonds on top. Why? Because of the shape. Because of the shape of the orbitals, you have the pi bond above and below the plane of the nuclei, and then you have sigma bonds between the 2 atoms. So the sigma is between carbon, and then the pi bonds are above and beyond, right? But before we get there, before I show you a bit more, let me show you. Let me give you another question. So we have, I think we have 5 already. Yeah, we have 5. Okay, so six is, what is the hybridization in CCl4 CCl4, PCl3, and OF2, right? What is the hybridization? That's number 6. So you're going to tell me what is the hybridization among these, right? That's number 6, right? But let's get back to sigma and pi bonds, right? So again, as I was saying, the sigma bonds are in the middle, the pi bonds are around the carbon. So this is how we make double and triple bonds. So the question that I like to ask is, hey, among these, which are the sigma bond, which one is sigma, which one is pi, right? When you have a single bond, it's a sigma bond. When you have a double bond, you usually have 1 sigma and then 1 pi bond. And remember, the pi bond is around. And then when you have triple bond, you have 1 sigma and then 2 pi bonds around. So if I give you a molecule, I can ask you like, hey, how many bonds are sigma? How many bonds are pi? All right. And then you will tell me. So you will count the single bonds, and these are these are sigma bonds, right? And then you will count so you will count one pi bond in a double bond and 1 pi bond in triple 1 pi bond in a double bond and then 2 pi bonds in a triple bond. So the next question that I'll ask you is, how many sigma, so that's number 7, and pi bonds in C2H2. All right, so you're gonna tell me how many sigma and pi bonds are in a molecule of CH2H2, and if you know, as you can imagine, you're gonna have to draw it first, okay? All right, so let's talk about one last thing before we end this lecture about chemical compounds and their geometry. Now, the last thing that I want to talk about is doing good on time. We're just 40 minutes in. So I want to talk about molecular orbital theory. So this is still the same idea, right? This is still the same idea, but we still want to understand a bit more of what happens when we combine two atoms, right? What happens when you combine two atoms? We already seen what happens when it comes to their Lewis structures. We already seen what happens when it comes to their geometry. Now we've just seen what happens when it comes to their shape, right? Because this is the real shape of electrons when it comes to orbitals, right? Now let's look at their electrons, the electrons and electron levels. So if you remember back in Gen Chem 1, you learned about how, right? You learn about how whenever you have like an atom of hydrogen, for example, it will have one s, and one s will occupy a box of electrons like this, right? But if you have more than one electron, they are at different energy levels, and they can combine, right? So they can combine one way, right? So let's say 1s combines with 1s, right? When they can combine to make two electrons in a box like this, but sometimes we do what we call destructive interaction, where whenever they combine, they cancel out, where you don't have any bonding, right? But here, when they combine and they give you two electrons, this is how you form a sigma bond, right? This is how you form a sigma bond. So we already seen bonds, we're just zooming in to see really what happens. And it can get confusing, guys, but to kind of give you a quick way of like how it becomes a destructive interaction is because we think of electrons as particles and waves, and you know, there's a whole world of what we call quantum theory. We're not going to talk too much about it, but if you add two waves together, they can either add up to give you a bigger wave, or they can cancel out to give you no wave. So that's why it can be either constructive or destructive, and that's why whenever we combine two electron orbitals, they can either give you a bigger orbital or they can give you no orbital. But don't worry about that, don't think about that you don't have to know, but you know, this is kind of what we're talking about, right? But again, the same thing happens with p, right? The same thing happens with p orbitals. Whenever they combine, they can cancel out, or they can make a bigger orbital, right? So whenever the two things combine, we can either have this or that, right? And they can give you a sigma or pi, right? We already talked about this, right? If they will give you a sigma bond when it's a bond here, they will give you a pi bond because again, you have how do I say this? P orbitals are both, so they have two shapes. They have like a straight up face and then a horizontal shape. The horizontal shape will give you the sigma bond. The vertical shape will combine to give you pi bonds. So this is how we make double bonds, guys. All right, so again, this is called molecular orbital theory. And I want everybody to understand this. But a few things to combine, a few things to consider, a few things to consider, right? The number of molecular orbitals, right, is equal to the number of atomic orbitals combined, right? And then the more stable the molecular orbital, the less stable the anti-bonding. So these are kind of the theories, right? And then when you're feeling these orbitals, you go from low energy to high energy. And each molecular orbital can accommodate up to 2 electrons, right? And then we talk about this, but when adding electrons, we're going to use Hund's rule. And what it really means is that when you're adding electrons, you're going to add, you're going to start with filling out the empty ones, but we'll talk more about that, right? And then the number of electrons in the molecular orbital is equal to the sum of electrons on the bonding atoms, not the anti-bonding, right? So let's put that into practice to see how it looks like, right? So let's say I ask you like, hey, give me the molecular orbital, and this is how I'm going to ask. Give me the molecular orbital energy level diagram for, I don't know, N2, for example, right? For N2. And the way you're going to structure it is you're going to start with 1 here, right? So this will be 1n and then 2 n's, and then you're going to tell me how both of them combine, right? And then how do they combine? They're going to combine, right? So because these are 3p orbitals, right? They're going to combine to give me these 3p orbitals that will be either bonding or anti-bonding, right? And they will be, for p, it will be 2 pi bonds and then 1 sigma bond, and then there will be bonding and anti-bonding, right? So you have bonding and anti-bonding orbitals, all right? So this is kind of putting these together and how they would look like and how the electrons will bind in these orbitals, and they will start again, they will start at the low energy, right? So they will start at the sigma energy, right? And then you will go up. So this is how you go up depending on the electrons you have, right? So for example, lithium has 2 electrons. So if lithium has 2 electrons, right? So let's do N. We already just said N, right? So N, think about it this way. How many electrons does nitrogen have? That's right, 7, right? You should have you will have an a periodic table, so it should be good. But 7 electrons. So your role is, okay, now that I have 7 electrons, how are they going to stack up? I'm going to fill out all of the electrons, all of the 7 electrons, right? And then I'm going to fill them up on N2, right? And if you remember how N2 combines, it doesn't combine these 7 electrons, right? The valence electrons are what on N? Do you remember what the valence electrons are on N? 5, right? 5 electrons are the valence electrons. If you remember, N is like this. 5 valence electrons. So your role is we're going to put the valence electrons to their energy levels. And if you confuse on how the energy levels add up, they add up this way, right? We start with the sigma, and then sigma antibonding, and then you go to pi, right? So sigma S, the sigma S, sigma antibonding. So we start as S. Why? Because S is the lowest energy level, right? So you start at S, then we go to P. So where is S? They don't have it. Okay, so we start as S, and then we go to P. So we will start filling out. I actually like it this way, right? We start at S. So for nitrogen, we're going to start at S. S, we give it 2, and then antibonding S, right? And then we're going to go to P, right? And then we're going to go to sigma, right? So after that, we go to sigma, P, and then you keep going if you have more. And the Hund's rule was talking about how whenever you have like 2 extra, you're going to, if you have 2, you're going to fill out the empty ones first before you fill out both of them. Does that make sense? All right, let's see if I can find something that can illustrate this better. All right, so there are 2 ways to look at this, right? So one way is this. You have 2 orbitals, 2 atomic orbitals that combine together, right? 2 atomic orbitals that combine together. So let's say I have, so nitrogen, if I have 5 atoms of nitrogen, right, I can put them together like this, right? 5 electrons of nitrogen, right? I can be like, oh, this is 1, 2, 1, 2, 3, 4, 5, right? 1, 2, 3, 4, and 5, right? And then I can fill them out here as well, right? 1, 2, 3, 4, 5, right? And the nitrogen fills up with 1, 2, 3, 4, 5, right? So then you can think about it this way, right? They combine based on energy levels, and whenever they combine, you're going to fill out this one first and then this one, right? And then you go to P, right? P also combines by sigma first, right? And then pi later. So this is the order. So you can look at it this way. I like this diagram because it shows you the 2 things that are combining, the 2 electrons that are combining. But you can also use this as energy levels, telling you like, hey, we start at this one, go to 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 this one. So this is how you fill up electrons, right? And again, we call this molecular orbital configuration, right? So for number 8, so we're going to do just number 8. Number 8 is give the molecular orbital configurations of H2, O2, and and NO, right? Let's see if we can combine N and O, because not only can we do molecular orbitals of just single diatomic elements, you can do the same for compounds. Let me actually give you more examples so that you understand this better. So this is the molecular orbital of O2, right? O2. And this is another weird way, but again, look. Oxygen has how many electrons? 8, right? But how many valence electrons? 6. So you have 6 valence electrons, and these are these ones, right? 1, 2, 3, 4, 5, 6. 6 valence electrons. 1, 2, 3, 4, 5, 6. 6 valence electrons, and then we represent them this way. And then the molecular orbital combinations, like how do they combine. And again, all you need to do is fill out the levels the way they go, right? So we start with this one, right? Go with this one, then we go to our sigma. For P, you go to sigma before you fill out pi. So you're going to fill out sigma, and then you go to sigma, pi, and then pi non-bonding. So again, you're going to go with these levels, right? These levels, just follow these levels, right? Sigma non-bonding, and then sigma 2p, and then pi, and then you go to pi non-bonding, and then before you go to sigma, right? So these are the levels, right? Again, if I give you a compound, right, any compound that I give you, you're going to fill out their valence electrons here, fill out the valence electrons here, and then show me how they combine here, starting with this one and then going up. That's it. That is it. So if I give you, like, this is CO, you can do the same thing, right? This is carbon, this is oxygen. You can combine them the same way, right? By filling out the electrons here, 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 right? And then you're done, actually, right? Because the numbers are 1 2 3 4 5 6 7 8 9 10, right? So you're done there. So you just draw the electrons on this side, draw the electrons on this side, and then you fill them up in the middle. Does that make sense? I hope that helps. So for these ones, whereas you give me the MO configurations of H2, O2, and NO, you're going to draw this diagram that's empty, right? You can draw it this way, but you can draw it this way as well. It's all the same, really. Or even you can draw it this way as well. It really doesn't matter as long as you have the right order. So you're going to draw the atoms here, right? So let's say, I'm not going to use the one that I gave you. So let's say you have F2, right? I asked you F2. F has how many valence electrons? 7, right? 7 here, 7 here. So you fill out 1 2 3 4 1 2 3 4 5 6 7, right? Same thing, 1 2 3 4 5 6 7. So you fill out 7 here, 7 here, and the total is 14. And then 14, you're going to fill them up with the right order, right? 14, fill them up with the right order. So the way they're going to fill out is in this order, right? Where you start with sigma non-bonding, P, and then you keep going, right? This is the order. I like this one. This is the order that shows you which one fills out first, right? Sigma non-bonding, and then pi, sigma, and then pi non-bonding, right? So it's going to be for sigma, give it 2 electrons, sigma non-bonding, 2 electrons, right? And then we're going to go to P, pi, 1 2 3 4, right? So we have 1 2 3 4 5 6 7 8, right? We have 14 electrons, so we gotta go to the next one. The next one is going to be, I think, after P, the next one is sigma 2p, and then pi, right? So the next one is going to be these two, so that's 10, and then after that we go to pi to give it 4, right? So 1 2 3 4. All right, so that's how you fill them up, right? So go ahead and do similar diagrams for H2, O2, and NO. This one should be easy. This one should be easy as well. This one might be a bit tricky, but you can do it. Again, lay out the diagram, count the electrons for both of them, valence electrons, not total electrons, and then follow the order that I gave you, right? Shouldn't be difficult, but if anything, in this chapter is a bit tricky. I would say is that everything else is very easy, but you can figure that one out as well. But that is it, guys. That's all I have for you today. That is molecular geometry, molecular orbitals, hybridization. Make sure that you understand this, because again, these will help us make sense of compounds, and we will use them in the future. But as usual, if you have any questions, if any of this doesn't make sense, I say, pause, rewind, replay, take good notes. But if you have any more questions, please reach out and I will be happy to explain this fully. And we are at 59 minutes, guys. All right, so I managed to put all of this within an hour. But again, if you have any questions, feel free to reach out, and I will see you in the next lecture. Bye-bye.